Our next speaker will be Francesca Miozzi, also from the Carnegie Institute, discussing laser-heated diamond anvil cell and synchrotron radiation to investigate planetary interiors, the example of the iron silicon carbon ternary system.
Good morning, everybody, for who is morning, and hi, everybody, for being here today. I am at the Earth and Planet Laboratory, but the work I'm going to present today is part of the work I did for my PhD at Sorbonne University, and more precisely the IMPMC lab. Before starting, I would like to thank the organizer of the workshop for putting together such an interesting program and for giving me the opportunity of presenting my work. I also have to thank my two supervisors, Guillaume Menard and Guillaume Fiquet, and all the other people that made this work possible. The data that I'm going to show today are data that were collected on several different campaigns at two main light sources, and so the SRF and precisely on line ID 27, and Petra 3 ring on Daisy campus and precisely the line P202. Compared to what has been done before from the other presenter, I'm going to kind of move farther away from the Earth, and I would like to show you how the combination of mineralogy and petrology can help us unveiling not only mysteries of the Earth, but also planets outside the solar system. So why our interest into these carbon-enriched phases is because in recent years, between all the stars that have been discovered outside the solar system, some have been observed to have carbon-enriched interiors. So we have here a plot of some observed stars as a C over O and mg over SI ratio. And along with the sun that stay here, we have many stars that are enriched in carbon. This is interesting because after a certain threshold of the C over O ratio, and precisely 0.8, planets are considered to have a carbon interior or potentially have a carbon interior. This information comes from condensation sequences calculated with thermodynamic models. And we have here two examples. So for a sun-like C over O ratio, so approximately 0.5, we see that the first mineralogical phases to form are silicates, the one we have on Earth, so like MgSiO3, Mg2SiO4. But on the other hand, in carbon-enriched environment, the first phase to form will be silicon carbide, followed by iron carbide, iron, and carbon. So this means that if we have planets orbiting stars that are carbon-enriched, these four phases might have a way more important role than they have here on Earth. So the purpose of our work was to make a set of experiments with the objective of providing reliable data on carbon-enriched systems. So like, what are the stable phases, the structure, the properties, and all this data would go into a toolbox that we could provide to people modeling carbon-rich exoplanets. And this would be useful for the interpretation of data coming from observation. So we started with the SSE binary system, and then we added iron and moved to the ternary FESSE system. The sample used for all the experiment were thin film of non-stoichiometric deposition realized by PVD, so physical vapor deposition. These samples are exceptional for diamond anvil cell experiments because they are all at the same thickness. They are homogeneous at the nanograin scale. It's possible to choose the wanted stoichiometry. They couple really well with laser, and it's possible to observe optically where is the heating spot. So that's very nice for like experiment recovery. And finally, they have all the same thickness. And with one sample made by PDD, it's possible to have multiple samples for a dark experiment, and this guarantees the reproducibility of the diamond anvil cell experiments. So all the experiments were done in laser-heated diamond anvil cell. We used gas-driven membrane diamond anvil cell with rhenium gasket and KCl as a pressure calibrant and pressure medium. All the experiments were performed between the 20 and 200 GPa range and below 4000 Kelvin. And as Rebecca said in her presentation, we had multiple heating spots for each samples. So we were able to collect approximately 18 heating runs on the two systems, so both the binary and the ternary system. So, and when possible, the sample were recovered after a diamond anvil cell experiment. A transverse cut of the heating spot was exposed with a focused ion beam, and then scanning electron microscopy analysis were performed to confirm the observation in diamond anvil cell and to observe if there was the presence of phases that would have been hidden in the diffraction pattern. Moving to the result on the binary SiC system. So SiC is known to have a phase transition from a B3 to a B1 structure at high pressure. The structure is still cubic, but there is a change in the coordination of the atoms. And it was known in literature from the 90s, but it was never well traced in the pressure and temperature space. So with our data, we were able to define the transition zone and the Clapeyron slope of the transition in the temperature and pressure space. So we have here this figure that represents part of the data we collected on SiC, and the one with the double color are the point in which we observed both phases stable together. It's also important to notice that this transition is associated to a 10% volume reduction that might have very important outcome when these data are applied to planetary interiors. And we can see here, these are volume over pressure data. This is the B3 structure, this is the B1 structure, and the difference in volume is well visible. We moved on then, trying to determine the thermal equation of state for the B1 structure, that is the one that is fundamental to model planetary interiors, because we are speaking about, if we're speaking about higher pressure. So we have here as volume over pressure, all the data we collected at high pressure and high temperature on the B1 structure. And we can see how the compressibility of this phase is closer to the one of diamonds than the one of silicates. We also tried to determine the phase diagram for the SiC system. And we did so by using samples with different stoichiometry. So either enriched in silicon, either enriched in carbon. What we discovered was that we didn't observe an intermediate compound, or we didn't observe any dissociation of SiC into Si plus C. But what we observed was one melting point in the silicon-rich side of the system and no melting point in the carbon-rich side of the system. So the assemblage SiC plus carbon was stable in all the pressure and temperature range. We then moved to the ternary system. And in this case, we wanted to explore the iron-rich side of the ternary phase diagram. So we are looking at the iron-rich corner. The aim was to determine which are the stable phases, which are their properties, how they interact with each other, how they react together, and possibly the melting temperature and melting relation. I'm going to present the result now as temperature over pressure figures to display which are the stable mineralogical assemblages for each samples. I will start from the one with the lower light element content, and we can see that in this case, only iron is stable at low temperature as the only phase. We have exsolution of an iron carbide with a low carbon content at higher temperature. So we have iron plus Fe3C. And this carbide is the first phase to melt, leaving iron plus a liquid after the solidus. We can notice how, as no other phase is stable together with iron at lower temperature, all the silicon and carbon should be in solution in the structure of the iron. However, this solubility of the two light element in iron is maintained also at higher temperature. As a matter of fact, if we plot the volumes of our iron, that are the triangles with green color, and we compare them with the volume of pure iron, that is the dashed line, and the volume of FeSi, that are the squares, we can see how there is an increase in volume in all the pressure range. So this is justified by the fact that all the silicon should be in the structure of the iron, and part of the carbon might be in interstitial position into the iron, determining the expansion of the unit cell. Moving to a sample with higher light element content, we see that in this case, we stabilize an iron silicide, so we don't have pure iron anymore. And the iron silice is stable as the only phase at low pressure, so all the carbon should be in solution in the structure. And we exsolve an iron carbide with a higher carbon content at higher pressure, so above approximately 30 GPa. If we move on and we increase the silicon content and decrease of 1 atomic percent the carbon content, it's extremely interesting because we see that in this case, we have an FeSi phase with stable as the only phase up to 110 GPa, meaning that all the carbon should be in solution in the structure. And then we have the exsolution of Fe7C3 as the iron carbide after 110 GPa. Finally, if we increase, like in the sample with the higher light element content, we have the stability of FeSi plus Fe7C3 in all the pressure range. So we have 4 composition, and these 4 composition, each one displays its own particularity. Moving on to the melting curves, we have, no, sorry, there is another data before. So we, as we have seen, the comparison of the iron volume with the other volume from literature allow us to see that there were elements in solution. So we did the same work also with the FeSi and the Fe7C3. And the FeSi, it was more important even because FeSi is a non-stoichiometric phase. So we compared our sample with data available from literature, and we can see that not only our sample have a different volume between each other, but they also plot on the line that represent the data coming from literature. However, this information can't be used as a reliable information regarding the stoichiometry of the FeSi, because in these data are those in which also carbon is in solution in the structure. So it's not possible to define if the difference in volume is given by the different stoichiometry of the FeSi or the presence of carbon. For the Fe7C3, instead, we can see how all our data plot together on this kind of the same line, and they also plot together with those from literature. So in this case, there is no solution of silicon into the structure of the iron carbides. Moving on to the melting curves, it was fairly particular because we saw that the melting curve of the sample with the lower light element content was different from all the others. So the 3 samples with the higher light element content had similar melting curves, that is represented in this figure with the orange dashed line, and is different from the one of the sample with lower light element content. As a matter of fact, the melting curve for this sample plot exactly on the melting curve of FeC that we have here in blue. And what is interesting to notice is that if we take 50 GPa as a reference temperature, the melting temperature for the alloys is different. So this sample melt below 2500 GPa, while all the other samples melt above around 2500 GPa. So this means that we should expect to have at least 2 invariant points in the ternary system. And this makes sense with the observation of the binary FeC system, where at least 3 invariant points are expected. Finally, we have here some of the images we did with the scanning electron microscope on the FIB cut. We have the sample and the pressure medium, and these are 2 different compositions. And it was possible to observe these darker patches Considering the chemistry of the system, these patches could correspond to carbon or silicon carbide. And this chemical mapping on carbon and silicon allow us to distinguish them as diamonds. As a matter of fact, where we have this bright spot in the carbon map, we also have these very dark patches in the silicon map, and that's enough to tell us that these are diamonds, so they should be considered in our recreation of the ternary system. So if we put together all the information that we have collected about the phase stability, the melting temperature, and the phase solubility, we can try to reconstruct the ternary phase diagram. So we have here some isothermal and isobaric section, starting at 2100 Kelvin, so where everything is in subsolidus state, and then increasing temperature. Here we have a zone where there is solubility of light elements in the iron, given by the sample with the lower light element content. And we have a zone where there is solubility of carbon into the FeSi structure, given by the sample that is stable as pure FeSi up to 110 GPa. We then reconstructed the stable phases using the rules of phase diagrams, and we could see that it corresponds to what we observe in our experiments. So we have these 2 other points, and in this case, the presence of carbon is corresponding to the diamonds that we observed in the transverse cut of the samples. When we reach 2350 Kelvin, we are slightly above the melting temperature of the sample with lower lead element content. So we start forming a melting pool, and we have the equilibrium of solid phases with a liquid, and this equilibrium increase at higher temperatures, so above the melting temperature of all the other samples, where we have a bigger melting pool with a smaller field of equilibrium of a solid with a liquid. But why we are interested in understanding the properties and understanding which are the metallic phases? We have seen it with all the previous presentation, but basically what happened during differentiation of a planet affect what are going to be the properties of a planet. And in particular, knowing the composition and properties of the metallic phases give us great insight into which might be particular properties of the planet. For instance, the properties of the core are those that determine the presence or the activation or not of a dynamo, and consequently the activation of a magnetic field. On the Earth, the existence of a magnetic field is fundamental to prevent the stripping of our atmosphere from the solar wind, but also in exoplanets exploration, it will be even more important, not only for the implication for the atmosphere and the planet, but also because if we are able to observe a magnetic field, we can kind of try to trace back what is the composition of the core, because if we know that certain composition doesn't activate a geodynamo, we can directly rule it out. So it's extremely important to have a clear view of all the processes involved with the formation of core. So I try to apply the data we collected in this study to see what would come out if applied to planetary interior. This is a projection in temperature of the ternary phase diagram I showed before. And we can see that this is the eutectic point, and the composition was determined by Rietveld. So this was the melting point for the composition with lower lead element content. We have here another invariant point and the temperature of the melting point of all the other phases. And we expect to have a third one here following what we know from the binary FEC system. So what is possible to see is that these 3 points create a kind of division in the phase diagram that separate a field in which FeSi will be the first phase to crystallize, a field in which some sort of iron carbide, so Fe7C3 or Fe3C, will be the first phase to crystallize, from a field in which we are in an iron-enriched composition, so iron would be the first phase to crystallize. I have drawn here a synthetic representation of these 3 different compositional domains, and I'm going to proceed now showing what we think it can happen if we consider our core composition as part of one of these fields. So we are estimating the solidification processes in a core that would be an FeSiC, from an FeSiC alloy with different composition. And as usual, we are considering the adiabat crossing the melting curve at the center of the planet. So in the first case, if we take, for example, a composition in the iron-rich side of the ternary phase diagram, we will have an Earth-like situation. So iron crystals forming and sinking due to their higher density. This sinking will proceed, starting to form a layer at the bottom of the core. And in the meanwhile, will promote solutal convection that is known as an efficient driving force to start a geodynamo. And this case is the bottom-up case. That is what we consider being the solution for the Earth, let's say. If we consider the opposite case, we are in the FeSiC field. So we are crystallizing an alloy in which the first phase to form will be iron carbides of some sort. In this case, we can expect the iron carbides to float back upward due to their lower density compared to the remaining liquid. And here, because the temperature is still higher, they will remelt and enrich the liquid in carbon. When the liquid will reach the saturation limit of carbon, we will start to form carbides, ideally, and this will create an upper layer. So this is a top-down crystallization style. And in this case, many questions are possible, because would it be possible to activate a dynamo if the solute convection is not strong as in the case of the iron? Or like if we get enough time to form this conductive layer on top, and we have a magnetic field. Does it shield the magnetic field? So it's still not useful to help the planet in its own. These are all the interesting questions that I hope will propel some discussion. Finally, if we consider the FESI field, is even more strange, I would say, or interesting as a scenario, because the density difference of the crystals forming in the FESI rich field wouldn't be so much between the crystals and the liquid. So probably the crystal will float around their position without either sinking or floating upward, freezing as a crystal mush. So in this case, I really can't say, like I can't even figure what would happen on the term of solute convection and further development of the core. I also want to show how we can apply the data on SiC. So this is an application of carbon-enriched planet, and this is a model that I did in collaboration with Caroline Dorn, and she's an exoplanet person. So we wanted to see if we can apply mineral physics data to exoplanets model, and we decided to model a planet made by SiC, so with a mantle of SiC, and a core that was pure iron. The dimension of the core was chosen to be the same as the Earth, and to have the Fe over SI ratio of the solar system. So we have these two possibilities. We have here a mass radius plot. So we have the evolution of radius for different mass for different planets. We have pure compounds, pure SiC, OMG, SiO3, and then we have some planets. Within all, we have the Earth, that is this dashed line, and the two green lines are the two planets we modeled. It's important to notice how for the solar FESI planet, let's say, the density is way different from the others. The evolution of the mass radius plot is way different from the other. But if we consider the planet made by pure SiC as a mantle and a core similar to the one of the Earth, is fairly close to the Earth-like curve. So what does it mean? It means that for certain observed exoplanets, the mass over radius plot, that is one of the main tools we have now to interpret observation, can't really help, because the same point, let's take for example this one, this is an observed planet. So this planet, if we consider the error bar, can be either Earth-like, either carbon-rich, and we wouldn't be able to distinguish. So where does this lead? This implies that we can't really stop at knowing the mineralogy of a planet and the physical properties, but we have to go deeper. We have to understand how the phases interact with each other, which are the density contrast, and which are the dynamical processes. And this, I think, can be done at the current state, combining the mineral physics approach, so understanding the properties of phases in a huge pressure and temperature range, collecting several points, combining it with petrology, so way more complex system than the one we use in mineral physics, because in mineral physics we start from the simple one and then we complicate adding variables. While in experimental petrology, usually we represent a composition and we study how it is at one pressure and one temperature. So we have a snapshot of that planet at that condition. So for where we are now, I think that the only way to get integrative model for exoplanets, and also like for the Earth, is to really connect what we can do with mineral physics and what we can do with large volume presses, both ex situ and in situ. But then if we want to speak about the future, as I was saying, and as everybody said, everything is related in planets. So the surface interact with the deeper layers by tectonic, by other conditions. And what happened in the deep Earth or in the deep interior of planets affect also the evolution of the old planets. Let's say, for instance, the example of the dynamo. So we can't really limit to analyzing one properties or one thing, but we have to try to get a complete view of a planet and how all the parameters interact with each other. So we have to increase the chemical complexity for what concerns exoplanets and overcome technical limits. And on this, I have put together a couple of slides of what's my dream, mainly on synchrotron techniques. So the first one would be to have higher resolution and routinely reach higher pressure, like 3 megabar, 4 megabar in diamond anvil cell, and amazing isothermal isothermal plot with data from 20 to 300, 400 GPa in order to really be able to model the interior of planet without extrapolation or with not so much extrapolation. And then moving forward to having 3D information of chemistry and morphology, we have seen that also Faye has shown us some of the amazing reconstruction. So I think that's where we have to go to have a complete view of each experiment we are doing. Then the other aim is to actually extend what we can do now in large volume on synchrotron, so online. So all the experiment about percolation, deformation, falling sphere experiment, all these experiments that allow us to see how things evolve in time. So the time parameter together with the pressure and temperature, it would be amazing to extend it to diamond anvil cell. And I'm sure we will arrive there. We already have tomography in diamond anvil cell, but it's like high pressure tomography, but we're missing the temperature component. And there was this paper from Wendy Mao suggesting that this is the next development for synchrotron techniques. And I hope that's where we will go, because once we can couple X-ray imaging and diamond anvil cell and laser heating, I think we can really do amazing things to understand planetary interiors. With this, I thank everybody for the attention. I'm here if there are some questions, and that's all.
Thank you, Francesca. It looks like we have one question so far in the chat, and then I have a question otherwise. Suki Dorfman said a 3 to 10 microns is thick for a thin film. Was this challenging in the deposition?
Yes, we actually had several batch of samples with different thickness. These samples were done from a company, and they weren't used to make samples for earth sciences. So it was, when doing the position is also challenging because we can't go thin, we can't go super thin, because then it becomes difficult to detach the sample from the substrate where you're depositing. And at the same time, you have to make them not thick enough for the diamond anvil cell. So in particular, this sample, we didn't deposit them ourselves, but I guess it should have been difficult because they send us tons of samples, and of which very few had the right thickness for these studies. I don't know if this answered the question, but in case we cannot discuss later.
Sure, and I have one quick question. Regarding your complex phase diagram, did you report these on heating as well as cooling? Specifically the phases that include solubility of silicon and carbon?
Yes, the comparison of volume comprehend both heating and cooling run. So the solubility is observed in all the pressure and temperature range when we are comparing volumes. Of course, we consider also the quench kind of more reliable, I would say.
Awesome, thank you.